Good morning or afternoon, folks. Happy Thursday. Today's target is to be able to write the electron configuration for any element in the periodic table. On Tuesday, I had you guys creating orbital diagrams where we were drawing little arrows representing electrons on various lines representing the electrons in an atom. I recognize it's kind of a weird way to think about it, but basically, the lower down we are in our electron hotel, the closer those electrons are to the nucleus. And the higher up we go in our electron hotel, the further away electrons are from the nucleus. This is a really good visualization of the electrons in an atom. However, it can take a long time to create. And it's also a little bit confusing. What's with these 1s's and 2p's and 3s's and that type of thing on the sides of these diagrams? They don't seem to make a whole lot of sense. So what's going on there? That's what we're going to be diving into today. So the first thing that we understand from our unit with protons, neutrons, and electrons, and just understanding how an atom is organized, is that atoms are fundamentally different depending on what element they come from. And a great way that we can see this is visually. If we are to take what's called these really powerful microscopes and zoom in on the atom so we can actually see it, we actually get these really cool and weird and bizarre shapes that form based off of the number of electrons and their charges and their spins and all kinds of information about them. We get different shapes. We get sometimes circles. Sometimes we get these sort of dumbbell shapes or these double dumbbell shapes. And we can get some really cool and interesting phenomenon that happens when we really zoom in on the atom. These are what different elements, different types of atoms look like when we zoom in on them with our really powerful microscopes. Okay, so why does that matter? Well, it matters because sometimes we need to be able to identify the electron configurations or the locations of electrons in atoms. That's really useful and powerful information in science because electrons influence reactions. Okay? If we know where the electrons are, we can predict what they will react with. And that's very powerful information. So we're going to dive in and learn how to do that. Okay. So the first thing is just kind of understanding the shapes of all of the different elements in our periodic table. So depending on where an element is located in the periodic table influences the type of shapes that that element will create. Elements in the S block form circles. Elements in the P block form form those kind of dumbbell shapes. The D block tend to form double dumbbell shapes. And the F block forms some really fascinating, sometimes donut-shaped patterns. They're very cool. But all of these different elements form different shapes. And so they were organized into different blocks to kind of help categorize the shapes that they tend to create. Additionally, we can organize elements into energy levels. So the first level of our periodic table is the first energy level. Then the second, the third, the fourth, fifth, sixth, and so on and so forth. One little nitpicky note is that when we get into the D block, the energy level shifts a little bit. So the energy level shifts from 4 to 3. And these numbers and these letters, that's where our orbital diagram levels came from. The different energy levels in our orbital diagrams come from the elements themselves. They come from this periodic table. Okay, so now that we've gotten into our history, now that we know where all of this comes from, let's take a little bit of time and understand how to actually use it. How can we figure out what the electrons look like for individual atoms? Okay. So our first example is with hydrogen. Hydrogen is a great example because it's the first element in our periodic table. Hydrogen is in the first period, the first row, the first energy level. And so when we're writing its electron configuration or its electron address, kind of like where it's located in the periodic table, we'll start that off with the energy level, 1. We'll then follow that up with the block that it comes from. And then finally, the column of the block that it is located in. So hydrogen's electron address is just 1s1. If we were to have an orbital diagram, there would be 1 electron in the 1s level. Okay, let's try a little bit more challenging problem. Let's try oxygen. So oxygen is a little bit harder. Whenever we're writing something's electron address, we have to write the entire address. It can be really tempting to just kind of like skip to the end or something like that, but just like with Google Maps, you need all of the instructions. And just like with an electron address, we need to take into account all of the electrons an atom has. So the very first electrons that oxygen has, the electrons that are closest to the nucleus, are the 1s electrons. See, these 1s electrons right here, they're like in our first energy level, that first ring close to the nucleus. And there's 2 of them, and they're located in the 1s energy level. Oxygen's next 2 electrons are located in the 2s energy level, and its last 4 electrons are located in the 2p energy level. See, 2 in this purple section is p. 1, 2, 3, 4. So, remember, whenever we're writing something's electron address, we always start at the beginning. A really good way to do it is just to read the periodic table like it's a book. So for oxygen, we're starting at the top leftmost page, and hydrogen and helium, they are 1s2. Lithium and beryllium, they are 2s2. And then we get to, this is boron, carbon, nitrogen, and oxygen. They make up the 2p4 because they're in the second period. They're in the p block, and there's a total of 4 elements or 4 electrons that bring us to oxygen. All right, let's give you guys a practice problem to see how you do. So what we're going to do, and we'll kind of do this one together, is we are going to try and draw the electron configuration for sodium, Na. Okay, so what is the start of our electron configuration going to be? What's just like the first piece of our electron address? What are we going to start with? Cool. We always start at the beginning. We're reading our periodic table like a book. We're reading our electron address, our MapQuest, our Google Maps to understanding the electrons in an atom. 1s2. Because there's a maximum number of 2 electrons in the first energy level. Okay. All right. So then the next 2 electrons, they are 2s2. Because we can house a total of 2 electrons in that s energy level, and it's in the second period. Okay. All right, so after elements 3 and 4 come elements 5, 6, 7, 8, 9, and 10. And they're in the 2p group. So it's 2p6. Okay. So, okay, why is it 6 instead of 2? Well, let's think back to our orbital diagrams. When we were looking at our orbital diagrams, the S groups, they only had 1 room for our pigs. But when we got to a P level, we had 3 rooms. And each room could hold 2 pigs or 2 electrons. So, when we're writing our electron configuration, the 2p group, 3 rooms with 2 electrons each, has a maximum of 6. And there are 6 elements and 6 electrons in that p group. Interesting. Okay, so we're learning a little bit not only about electrons, but about how the periodic table is organized. When we get to our third energy level, our third row, our third period, we encounter the 3s group. Now here's where a lot of people tend to make some mistakes. What number do you think should go after the s? It's 1. Because sodium is in the first column of the s group. If we were talking about magnesium, it would be 3s2. But since it's in the first column of our s group, it's 3s1 because it's the first column. It only has a total of 11 electrons. That makes sense, right? It's the 11th element. Its atomic number is 11, so assuming it's not an ion, it has 11 electrons. And in our electron configuration, we've got 2 plus 2 plus 6 plus 1 for a total of 11 electrons. Friday's assignment is some practice problems. Good luck. There will be an answer key provided. I'll talk to you guys on Monday. Bye, folks.